Hello everyone. In this video, we continue our discussion of clustering methods. As a reminder, clustering methods aim to partition a data set, and this data set is unlabeled, meaning that we only have a set of features. And we divide this into clusters or groups in a way that data points within the same cluster are more similar to each other than to those in other clusters. And therefore, a very important piece here is this definition of similarity between data points. And based on the way that we define this similarity measure, we can have multiple ways of defining a cluster. For example, in K-means clustering, which is one of the most popular clustering methods we have already discussed, the main assumption is that each cluster has one representative or centroid, and all other data points within that cluster are uniformly distributed around that centroid. So that's the main assumption that we make. However, in many cases, this may not be the best assumption because we might have, for example, elliptical clusters or clusters that they do not satisfy this simple assumption that we only have one representative per cluster. Therefore, in this video, we talk about two other clustering techniques. One method is called density-based spatial clustering of applications with noise, and this is usually called DBSCAN. So here we have the full name, but we really call this DBSCAN. And one important thing you need to remember here that this method uses a spatial clustering, meaning that it defines clusters as areas of high density. And this allows us to be able to find clusters of different shapes. We are not only restricted to spherical clusters as in the case of K-means clustering. And then we talk about Gaussian mixture modeling, which is a very popular statistical technique. And the idea is very simple. We assume that each cluster is coming from a Gaussian distribution, and this can be in high dimensional spaces, meaning that we extend this from univariate to multivariate spaces. So now each cluster has a mean vector and a covariance matrix. And finally, in this video, we talk about evaluation metrics. We have already discussed these internal measures, such as silhouette score or silhouette coefficient, which is this coefficient is based on the cohesion and separation of clusters, meaning that once we partition data into clusters, we want all the data points in the cluster to be as close as possible. So that's the idea of cohesion. And then data points from different clusters to be as far as possible. And that's the idea of separation. But one thing that we're going to focus in this video is this idea of external measures, meaning that although we are not using ground truth labels or true labels during model fitting or training when we have clustering techniques, we can still assume that we can use them during evaluation as sort of like a baseline to compare with the obtained clusters. And one way that we can do this is using this metric called Normalized Mutual Information, or NMI. So let's look at one of the examples that we had with K-means clustering before. So in this case, we have an unlabeled data set, meaning that each data point we have two features, x1 and x2. And although here we can see that, yeah, possibly we have 5 clusters, we want our, for example, K-means clustering technique here to be able to tell us which data points belong to the same cluster. And this is based on this spherical assumption, meaning that each cluster has one centroid, and then we have a scattering of these data points within that cluster around the centroid. And here, for example, is the result of our K-means clustering, where we are color coding to see data points that belong to the same cluster. And then we discussed the idea of what we call it as the elbow method to tell us what number of clusters is the optimal choice if we don't know exactly the true number of clusters in our data set. And that's sort of like, what we discuss here. And we figure out that actually 4 clusters in this case make sense because these 2 clusters are very close. So this does not cause any major issues in terms of cohesion and separation since these 2 clusters are very close to each other. And you can even see that when we look at the silhouette score, which is the internal measure that we discussed, this 4 has the highest silhouette score, which means that it's the best possible one according to this metric. So now let's talk about DBSCAN. So this algorithm, as we just mentioned, defines clusters as continuous regions of high density, right? So it should be continuous regions, and also it should be high density. So how do you define density? For each instance or data point, you count how many samples are located within a small distance from that data point. So that's what we call it as the epsilon neighborhood. And if we have at least these mean samples in this epsilon neighborhood, then we call that instance a core instance. So that's the idea of area of high density, meaning that we want to have enough data points in that epsilon neighborhood. So you literally, if it's a two-dimensional space, you gotta draw a circle with radius epsilon around that sample. And all instances in the neighborhood of a core instance belong to the same cluster. And any data point or sample that is not a core instance and does not have one in its neighborhood is also considered an anomaly. To see how this works, let's look at a very famous data set for clustering methods, which is called 2-moons dataset. In scikit-learn, you can use make moons to create this data set. It's obviously an artificial data set. We provide the number of samples, the noise level, and then we're using a scatter plot to visualize this 2-dimensional data set. And we mainly focus right now on 2-dimensional data sets because we want to make sure that we can visualize the result. So you can see that this is a difficult problem because we have these 2 half moons, right? So in this case, we cannot really have only one center representative for one cluster and similarly another representative for the other one because of this highly nonlinear shape that we have. So in order to just check this, we're going to first apply k-means. It's easy to apply, so why not to check that? We're going to set the number of clusters to 2. Right now we know that we have 2 clusters and we fit, and then we look at the labels that we get from k-means clustering. And if I run this, you can see that, well, as expected, k-means clustering will put one centroid here and one here, and so therefore everything on this side is in one cluster and everything on this side is in another cluster. So that's why you can see this simple idea used in k-means clustering is not always a great assumption. But let's see how DBSCAN works. So remember, with DBSCAN, there are 2 parameters you really have to think about. Epsilon neighborhood, so how small or large this neighborhood should be, and the minimum number of samples that they have to be in that epsilon neighborhood. And now we're looking at the labels that we get from DBSCAN. So if you run this, you can see that this method now with these parameters can correctly cluster this dataset. However, we can change things, right? So if I increase epsilon from 0.2 to 0.5, what do you think is going to happen? So something that can happen is that if this is like one of the data points that we want to study and we create the epsilon neighborhood, now we can have overlap with the other cluster. So let's see if this happens or not. And this indeed happens. So because the fact that now we connect in some ways these two clusters, so everything is now only one cluster. And that's one of the advantages of DBSCAN in general, because you do not specify the number of clusters that you want to recover. You just mention the epsilon neighborhood and the minimum number of samples, and therefore you automatically infer the number of clusters. But let's look at the other side. What if now we make this epsilon very small? So instead of 0.5, we have 0.05. And if I run this, now you can see the issue. The issue, as you can see, is that now we have too many clusters. So this is one cluster, etc. And this can be also a problem too, because in many cases we don't want to recover too many clusters, right? We want to have the right number of clusters, which is in this case with these two parameters, 0.2 and 5. So you can see that this epsilon especially is extremely important, because if we set this to be too large, then obviously all data points are connected and everything is one cluster. And if it's too small, then we can see that we get too many clusters, because then we partition this data set more frequently than we should. The next method we want to cover here is Gaussian mixture models, or Gaussian mixtures. So Gaussian mixture model assumes that the data is generated from a mixture of multiple Gaussian distributions. So each cluster is a Gaussian distribution. And so the idea is that we want to estimate the parameters that we have for each Gaussian. So in this case, you can see that this small k is the index for cluster k, and we have k of them. So the uppercase k is the total number of clusters. We have normal distribution, and this is the mean vector, and this is the covariance matrix. So this is the extension of univariate normal distribution to multivariate. And this is because you might have multi-dimensional spaces. And these pi k's are what we call as the mixing coefficients for the kth Gaussian component. So if this pi k is high, this means that cluster k is dominant or highly represented in our data set. And if it's a small, means that we do not have many samples or instances from that cluster. And we already defined mu k and sigma k. And this normal that we use here is technically the probability density function, or PDF, of the multivariate Gaussian distribution. So you can see that if you want to compare this with k-means, now the main difference is that each data point may actually come from multiple clusters because of these mixing coefficients that we are using. Meaning that in k-means, we assume that each data point belongs only to one cluster, but now one data point may actually, with the case of the Gaussian mixtures, may belong to multiple clusters. And the way I like to think about this is exactly very much like softmax's course that we had for classification problems. Although we are not solving a classification problem here and we are focusing on clustering, the idea is very simple. If you want to find the probability that data point X belongs to cluster K, we can use the Bayes theorem or Bayes formula to first find the probability of X given K. So that's the probability of X given K. And then times probability of K, that's that mixing coefficient. And then we have to normalize this by finding this sum over all possible clusters. So I would like to emphasize is that in this case, each data point has what we call as a soft assignment, right? So meaning that we assign actually a probability to multiple clusters rather than a hard assignment as we did in k-means clustering. And therefore, in this sense, this model is much more powerful than k-means clustering, and k-means is actually a special case of Gaussian mixtures. In order to show how this works, we again going to use a synthetic data set to be able to visualize things. We use this data set called make blobs. We set the number of samples to 1000, and then the cluster centers here. And to make this more interesting, I'm going to also transform one of these clusters by multiplying x1, which is the data matrix, by these 2 by 2 metrics. And then we have another cluster, which is based on the simple spherical assumption. So in order to show you how this looks like, right, so this is our very nice spherical cluster. And then we have the two sort of like elliptical clusters here. And this is what makes it more challenging, because if I have to use, again, the k-means clustering, probably the centroid should be somewhere in between. And this whole thing will be clustered together, which is not the case, because obviously this is one cluster and this is one cluster. And you can see here these two, right, that we are creating two clusters here for x1, and then we transform these. So that's where we get these two elliptical clusters. And in this case, we're also going to use Gaussian mixture from scikit-learn.mixture. So that's how you can find it. Because it's a mixture model, you define the number of components you want to recover. So here you have to specifically say how many clusters you want to recover. And then very similar to k-means, you can have different number of initializations, and then we do model fitting. And here is what is very interesting here, right? So here you can look at those pi k's or mixing coefficients to see if one cluster is more represented. You can see here, for example, the first and the third one are more represented than the second one. However, remember that in this case, the labels that we use, like 0, 1, 2, are assigned automatically by the clustering technique. So it doesn't mean that it should match with what we think is as the first or second cluster. And then we can look at the covariance matrices. So each covariance matrix is 2 by 2, and we have 3 of them because we have 3 clusters. And then we can use this fit predict model to look at the labels, or in this case, clusters that we recovered. And you can see, as expected, Gaussian mixture model is very powerful in terms of being able to recover these complex clusters. And I like to mention that in this case, you can see that these are the actual labels. But if you really want to know those, probability scores, we can do that too, right? So you can see in this case, this is for cluster 0, cluster 1, cluster 2. So data point 1 definitely belongs to cluster 2 according to these probability scores. The same thing here, and also for like the third data point, that belongs to cluster 0, and so on. So you can see that the nice thing here is that we have a notion of confidence because we have this P of k given x that we have in this equation here. So that's one of the advantage of Gaussian mixture model. The final thing we want to consider here is evaluating clustering techniques using external measures, meaning that when we have the ground truth outputs. This problem is very simple in classification problems because we have ground truth labels. These ground truth labels are used during training, and therefore this means that we have the alignment between true labels and predicted labels. So what we really have to check is to see whether the true labels are exactly equal to predicted labels, and if so, that's a correct prediction, and then we divide the total number of correct predictions by the total number of samples. However, in clustering, we do not have predefined labels, and we aren't using any labels during training because it's unsupervised learning. And therefore, clustering assigns data points to clusters without knowing their true labels. And you can always swap these cluster labels, meaning that you can say cluster A, cluster B, cluster 0, cluster 1, because that basically means all those data points are together, but doesn't necessarily mean if it's cluster 0, that should be the 0 that you have in your training data. Therefore, what we have to use is a method which is label independent. And one of the most famous one ones that you can use is this idea of normalized mutual information, which actually comes from information theory, which is a very nice area in mathematics and probability that you can understand the stochastic nature of many processes. So, in summary, normalized mutual information takes values between 0 and 1. 0 means no correlation between clusters and true labels, and 1 means perfect clustering. So we hope to get results that are close as possible to 1. And in order to explain how this works, the main thing that we have to do is to form something called contingency table, which is the equivalent of confusion matrix for clustering problems. So how does this work? You form a matrix very similar to confusion matrix that we had before for classification problems. And the Cij location here is the number of data points that belong to true class I, but were assigned to the predicted cluster J. So here, if I have two arrays, the first one is the true labels and second one predicted ones. You can see we have 4 zeros and all of them are assigned to cluster 1. So you can see that here we have true label 0, none of them clustered as 0, but all of them clustered as 1. And you can do the same thing here with the 6 ones that we have here. And you can see that we only have 1, 1, and the other ones are 1 to 0. So when we look at these, this seems to be bad because we don't have many terms on the main diagonal. But actually, the off-diagonal terms are here very good in the sense that it just seems that we have to change these cluster labels 0 and 1. We have to swap them. And then we have a very good match between true and predicted clusters. So we want to make this more formal so we can use this if we have more than two, classes or cluster labels. So in that case, we can find one number to summarize this entire contingency table. So the way we do this is by computing 4 things, step by step. Entropy of true label, and we showed that using the function h. So h means entropy, and we want to find entropy of true label, entropy of predicted clusters, and then mutual information, and then we normalize this, and that's when it's called normalized mutual information. So what is entropy? Entropy measures the randomness or uncertainty that you have in a distribution. So if I tell you that I have a random variable and that random variable can take only one value with probability 1, then the entropy is 0 because there's no randomness. But if we have, let's say, a Bernoulli random variable where it can take two values, 0 and 1, and then the probability for each is 0.5, then entropy is high because there's a lot of randomness here. So the exact definition of way we can calculate this is this negative sum of probabilities for each observation or each value that this true class can take on times the log base 2 of that probability. And then there's also a negative sign here. And these probabilities are very easy to calculate. You just use the basic definition of probability, which is the relative frequency of observations. So meaning that you can easily count the total number of samples in each true class and divide this by the total number of data points. So that's the probability that your data point belongs to that class I. This number of data points with label I over the total number of data points. So you can do the same thing for the predicted values or predicted clusters. So in this case, we use the same exact formula, except the fact that we do this for predictions, which means that now you literally have to look at the columns of the contingency table. And you look at how many of them are predicted as cluster J divided by the total number of samples. And the next step is now to find what we call as the mutual information. And so this is what it really tells us in terms of more information theory and probability is that how much knowing one random variable can tell us about the other random variable. And if you think about this true class and predicted cluster, we can look at their joint distribution and find this joint distribution log of joint distribution normalized by the probability for each class label and then cluster label that we have here. So these y hats, y hats are actually each element here. So each of these values that you can see here, right? So you can see that, for example, the joint probability that we get 0 and 0 is 0 because there's 0 here. And we can calculate this for the other ones. But remember, we have to do the proper normalization. That's how mutual information works. Okay, so then the last step is to divide this mutual information by the square root of entropies for the true class labels and predicted clusters. So to show you how this works, we're going to just do this manually and compare this with scikit-learn metrics normalized mutual info score. So this is what's already built in inside scikit-learn, inside the metrics module, like very similar to where we find accuracy score, other things for classification and regression problems. So we want to do this step by step and compare with this built-in metric. So very first thing, we want to be able to show the contingency table here for these true labels and predicted clusters. So this is what we create here, and we do this using pandas. We create two series and we use this cross tab, and this is exactly what this gives us. So now you can think of this actually as also as a numpy array, but I wanted to make sure that this has better naming strategy in terms of these true labels and predicted clusters. So one thing that we need to do to find probabilities of true labels, we have to find the sum across the rows, right? Because that's how it corresponds to true labels. So we do this by finding dot sum axis 1, and then we divide this by the total number of samples. And then we use that formula of negative sum of probabilities log base 2 of probabilities. So you can see that in this case, if you look at these PYs, it's 0.4, right? So 4 divided by 10, because we have a total of 10 elements, is this probability that y equals 0, and probability that y equals 1 is 6 over 10.6. And here we have high entropy because of the uncertainties close to 50-50. So that's why you get 0.97. We do the same thing now with the column. So that's why we use axis 0 of the contingency table. And in this case, it's exactly 50-50 because we get 0 plus 5, 4 plus 1, and divide by 10. And now the only other thing that we have to do here to find joint probabilities, right, is to divide each element of this contingency table by this total sum, and then put it in that equation that we have, that P, or the joint probability, times log 2 of joint probability divided by the individual probabilities. And so that's our mutual information. And in order to find normalized mutual information, we have to divide this by the square root of hy and the hy hat. These are the entropies. And in this case, we also use the scikit-learn version. So that's the one that we use, this normalized mutual info score. And we compare them together. And hopefully we get exactly the same results. Yeah, so you can see that our implementation gives us 0.6190, and that's exactly the same we get from normalized mutual info score from scikit-learn. So that's great. We know exactly how this works now. To wrap up this module, so let's look at the iris flower data set that we used before. So we know that this is a data set where the features are, we have 4 of them, like, features of a flower, sepal length, width, and petal length and width. So there are 4 features. And there are also like 3 classes here. So we have 3 species. So in this case, what we're going to do, we're going to apply k-means clustering to this data set, but remember, we only apply this to the input features. We do not use labels when we are training clustering methods. And we are applying this k-means clustering to all 4 features. And once we find these predicted labels, since in this case we do have true labels that comes with this data set, we can use normalized mutual info score. And now we can look at the labels. When we want to do this, obviously I cannot do this in a four-dimensional space, but instead I only focus on the first two features. So I can show you this in a two-dimensional space. And then obviously we're going to look at this normalized mutual information score too. So the normalized mutual information score here is 0.75, almost 0.76, which is respectable in the sense that it is, about 0.5 and like halfway through to 1. So if we had 1, that would be perfect. We know that this is a real world data set, so we probably cannot find a perfect clustering technique. And if you look at the actual sort of like partitioning of the data, you can see that overall these clusters are very meaningful. So especially like this one, that makes sense, and these two. The only issue that we have is that obviously we have these overlap between these two species, and so that's what makes it hard, regardless of whatever clustering technique they use, to be able to very accurately cluster or partition them. But this number that we get here and this two-dimensional representation really shows that this k-means clustering here is a good model.